In this video, I'm going to give a brief review of some very important facts about complex numbers that are going to be incredibly useful in physics. So again, any complex number can be expressed as follows. And I'm really going to give two ways that we can express our complex numbers. So the first that you often see is this, where A and B are real numbers, and then of course I is the imaginary number. I is the square root of -1. So any complex number can always be written in this way. And let's call it C, just to give it a name. So if C is a complex number, it can be expressed as a sum of two real numbers. So we have a real part. We'll often refer to this as a real part plus an imaginary part. Or we can express it in what's known as polar form. Known as polar form, often. Where again, R and theta are real numbers and I is the imaginary number. So you see, in either case, complex numbers are helpful because they carry two pieces of information. When you have one complex number, there are always two pieces of information contained in it because you have that real part, you have A, and then that imaginary part, B. So there's two numbers associated with your complex number. When we write it in polar form, we're just expressing those two numbers in a different way where we have R and theta being our two numbers representing which make up all of the information of our complex number. One important operation when you have complex numbers is taking the complex conjugate. So we usually, if we have C equals A plus IB, then the complex conjugate, C star, we just send all of our i's to minus I. So this becomes A minus IB. Or if we want to write things in polar form, then C star becomes RE. Again, just wherever you see an I, you send it to minus I. So this is e to the minus I. Oops, sorry, theta. Theta up top. And the complex conjugate is going to be very helpful because then we can calculate the absolute square which we'll write as absolute value bar squared, which is C star C. And this object is always going to be positive and real. Always. Positive and real. And you could see that very quickly. So if we calculate C star C, that's A plus IB times A minus IB, which if you just multiply that out, you can see that this is A squared plus B squared. Remember, A and B were both real numbers, and the imaginary I has gone away, and so we're left with something real. We could also calculate it in our polar form, where we have R e to the I theta, R e to the minus I theta. The e to the I theta and e to the minus I theta cancel each other out. They turn into 1. So this becomes R squared. And remember, again, R was a real number in our polar form. And of course, it's R squared, so you know it's going to be positive, right? So the absolute square, when we're talking about complex numbers, it's always important to remember that you don't just square the number, you have to multiply it by its complex conjugate. So that's going to be an important and useful operation. There's a very important formula called Euler's formula that we will use a lot. And actually, it'll help us to relate our polar form of complex numbers to our other form where we just have a real part plus an imaginary part. So Euler's formula says e to the I theta equals cosine theta plus I sine theta. I'm not proving this formula. You can look up all sorts of things about it. I'm just going to tell you this formula, and we're going to use it all the time. So right away, as I said, we can use this formula to relate our polar coordinates, our polar form of complex numbers to our other form. So if our complex number is r e to the I theta, then now we can use Euler's formula to say this is r cosine theta plus I sine, IR, r sine theta. And so then we can just read off this r cosine theta must be A, and then r sine theta is just B. So we can immediately use this to go back and forth between our polar form and then our A plus IB form. Sometimes it will also be useful to think in the other direction, so we can invert Euler's formula and find that cosine of theta equals e to the I theta plus e to the minus I theta over 2. And sine theta is e to the I theta minus e to the I theta, minus the top 2, divided by 2I. So you can invert that formula to find these two expressions, which are going to be incredibly useful identities. So I should also box these a bunch of times. All right, so those are some of the basic things from complex analysis, dealing with complex numbers that we're really going to need in physics. These are incredibly helpful. We can do, I'll just say, in physics, you could do things always with just real numbers, but using complex numbers really just makes things a lot better. And the power of complex analysis ultimately in physics is it's so powerful that it really is incredibly helpful in physics. I can't even stress it enough.